The Fall Academy signing back on. So today we'll be talking about how to prove the convolution theorem. Basically, if you apply an input onto a linear time invariant system, that we want to prove that the output is just equal to the convolution of the input times the output. So given that we have an LTI system, which stands for linear time invariant system, I'm going to draw it as a box. LTI. LTI, and this is a system, right? So given that we pass an input x of t onto the system, we want to observe the output of the system y of t as the convolution of the input with something called an impulse step response. So the first thing in our proof is we should represent x of t as an integral. So x of t is just equal to the integral from negative infinity to infinity of x of tau times the Dirac delta of tau minus t. The reason why these two expressions are equivalent is because tau fires at t is equal to 0, and since 0 is in an interval of between negative infinity and infinity, that means that the value of this integral should equal to x of t. So the idea is that we can represent an integral as a summation of finite elements. And the way this works is that if you have any arbitrary function, and let's say it spans from negative infinity to infinity, you can write the function as spanning from the difference between how often you want to sample the point in your function. So let's say you want to start sampling at delta. The next interval you will sample at is 2 delta, 3 delta, 4 delta, and so on and so forth. So the way I can represent this integral as a sum of finite elements is that I can say that this is equal to the value of x at k delta, where k represents going from delta to 2 delta, 3 delta, and so on and so forth. So k spans from negative infinity to infinity, and for each term, pause this, bro. So, I realized that I made a mistake. That the Dirac delta, it fires at t, not 0. Therefore, that's why it's equal to x of t. So essentially, any function could be represented in terms of a sum of finite elements, and this integral here could be written as a Riemann sum of x of k delta times Dirac delta of k delta minus t times delta, because delta in this case is our infinitesimal distance, and we sample the function, let's say, to the left each time, and each time we sample the function we multiply by the interval to get the area. And of course, as the delta goes to 0, you get the integral of this function. So the idea is that for a linear time invariant system, so now that I have represented the input as a Riemann sum, I haven't changed anything. And so what I can do is that, since I know that the Dirac delta function is an even function, I can multiply this by -1 and it won't have changed anything. So, and one thing is that I know that this Dirac delta is equal to the limit it's equal to the limit as epsilon goes to 0 of a unit step function, or of a rectangular function. And as you make this interval smaller and smaller, it jumps up to infinity. And so what I can do is I can represent this function as f of v, and I can say f of v of t minus k delta times delta of x of k delta, Riemann sum, and I can take the limit of epsilon going to 0 out of the summation. So in this case I have two limits, one to represent the summation as an integral, so I can take the limit as this infinitesimal separation between the sample points, so that I sample at a continuous time interval, so that I get the interval, and the second limit is the limit as this epsilon goes to 0 such that I form the direct delta function. So given that I have this input in this limit definition, I can pass this system into an LTI. I can pass this input, not system, I can pass this input onto an LTI system. And knowing that an LTI system is in fact linear, because that's the definition of an LTI system, then I can represent the output of the LTI system as a sum of the individual outputs, because the sum here represents the inputs, a sum of inputs. So if you have an LTI system, the output is just equal to the output from the individual inputs. Does that make sense? So let's say I have inputs x1 of t plus x2 of t. The output is the corresponding output is just equal to the sum of the individual outputs of each input, which is in this case h1 of t plus h2 of t, and so on and so forth. So knowing that I can do that, and knowing that an LTI system is also by definition time invariant, that means if I shift the input here, then I also shift the corresponding output. So knowing that for any LTI system, if I pass in the direct delta, I get an impulse response of that system, which I will represent as h of t. Then if I say that I represent the direct delta in the limit definition, f epsilon of t, as epsilon goes to 0, that means likewise I can represent the impulse response as a function, let's call it h epsilon of t, and it's defined, and the definition of it is when epsilon goes to 0, it forms the impulse response. So knowing all of this, I can cook up an ingredient. I can pass this system onto I can pass this input onto an LTI system, and the corresponding output, by definition of the LTI system, would just be equal to the sum of the it would equal to the sum. Since one more thing that I have to mention that is quite important is that x of k delta is a constant with respect to when I pass it into the system, because the system only depends on t, and since k delta does not depend on t, that means I can pull the constant out of the system. Because the system is linear, I can since this is a constant with respect to the LTI system, that means I can just multiply the corresponding output, which only depends on f epsilon, as just equal to the product of the corresponding constant x k delta times the output I've defined, which is h epsilon of t minus k delta. And the reason why this is the shifted input corresponds to shifted output is because the system is time invariant. And since the input can be represented as a summation of inputs, and that summation of inputs then can be passed into the LTI system with the shifted argument. Since if the input is a shifted argument, the output has to be a shifted argument, and that corresponds to this summation here. And this just is a consequence of the LTI nature of the system. So given that I have this output here, if I take the limit as delta approaches to 0, then I get the integral of x tau h of h of t minus tau d tau. And I know that this is equal to the input, which I said was equal to x of t. So now I've represented the output of the system, y of t. This is not equal, it's going into, I've represented the output as a convolution of x, the input, with the output. And that's it.